Hello and welcome to Lecture 8, Part 2. So, remember in introduction to this lecture, we were talking about arbitration, and we actually didn't quite get there. We talked about one hot encoding and priority encoders and how we could build those in various ways. Let's actually get to arbitration. And we're going to do that in two ways. We're going to spend some time studying the arbiter Chisel provides. We're going to go ahead and build our own arbiter, and then we're going to use our arbiter to build a crossbar. And we're kind of continually building up abstractions, components, and generators to build up more and more sophisticated pieces of hardware, right? So first off, what is arbitration? So arbitration is a situation where you need to choose who gets access, right? You have some sort of scarce resource. It could be one thing, it could be multiple things, but somehow you have more consumers than you have providers, right? Thus, you need some way to decide who gets access to that resource. And the word for that, of course, is arbitrate. And so if you have multiple simultaneous requests. Now, let's say, for example, you have a situation where you could have two people requesting something, but at this particular moment, there's only one requester. Great. Only one request, only one thing. Sure, give it to the lone requester. That's easy. Arbitration comes up when you need to handle ties, right? And it's like, we actually have multiple requesting at the same time and we can't satisfy all of them. How do we do that, right? And so, well, the arbiter decides. There's some algorithm inside the arbiter that determines when we have, multiple entities making a request, we can't provide all of them, who wins, right? And you can imagine there's different types of algorithms for this, right? You can have things like, fixed priority. So and so always outranks this other entity, right? And this makes sense. For example, in a processor, maybe you want to make sure your cache miss path always has priority getting access to DRAM because that way you can make your processor run faster. Alternatively, maybe you have something like a round robin to try and make it somehow more fair. And so it does depend on the situation. There's not always one size fits all for arbitration. Um, you see kind of different things. And so, for example, later on, you'll see we do like, another switch in the crossbar later on. I give you an example of the processors, but big picture, we're trying to build this device which takes requests for a resource, and if there's only one request, great, they get it. If there's multiple requests, it has some way to tie break. And without lots of generality, today we're handling the case of only one resource to grant access to. You can imagine you could have an arbiter which could grant access to two things to end things, right? It's that it could be more general. But for today, there's that one resource we're trying to control access to. So, very common hardware design pattern. So arbiters are, like many things, in the Chisel standard library. Um, Make sure the recording's on, by the way. Great. So how does it work? Well, as drawn below is this boxed arbiter. You have some number of inputs, which is parameterized. You have an output. Each of these inputs actually uses decoupled. So that way you can indicate, hey, is this request actually valid? And then the arbiter at the other end responds back to you. So even though this arrow is drawn one way, there's kind of that, ready signal coming back from the arbiter saying, you know what? Uh, did you actually get the grant? So that way the person who's doing the requesting knows did they actually succeed in sending something through. And at the other end, this out and out also decoupled. So it also has the ready valid signaling. So it also can, from whatever resource you're contending for, see if the resource actually is ready to receive a request. Likewise. So basically, if this resource over here is ready, that information, of course, finds its way into the arbiter. The arbiter, of course, will see many valids, people making requests. And then across those many valids, the arbiter uses this internal logic to figure out, who wins. And whoever wins will see the red signal coming back to them. So that way they get the right thing. And this is one of those cases I was talking about the other day and I was saying, be careful when you have a red signal depending on a valid signal. But in this case, it's kind of inevitable, right? Because the arbiter is not going to tell somebody it's ready if you're not even making a request, right? Because there could be multiple requesters. No point in giving the red signal to somebody who's not making a request. You want to see them making a request before you even give them a chance of saying you're ready. So watch out for combinational loops. Okay, I'll pause here for a second before we dive into example arbiters for any questions so far. Yes. Sorry, say that again. Yes. Yeah, exactly. Right. So every single one of these ports has their own ready and valid. Exactly. Yeah. This is one of the things where you can see with Chisel, you're starting to appreciate some of the advantages. There's nothing, groundbreaking here. It's just, yeah, we have all these ports. These ports can be declared with vec, end ports. We've seen that. Each of these ports can be marked decoupled, and you get the ready valid too. So you can see very quickly, not very many lines of code is generating a lot of wires, and these wires aren't wasteful. you would need those to run this by hand in Verilog. You still need that functionality. Yeah, so the good question about these different types of schedulers. So we can talk about a few of them, right? So the default one, Arbiter, which of course can go click at the chisel dock, um, fixed priority, right? So uh, there's a hard-coded priority or precedence, and according to that, if the higher precedence one request, they will always win. That can cause starvation issues. So then round robin, amongst those requesting, rotates who gets it. So this tries to be more fair. There's some subtleties about some corner case you can decide which is the right way to handle that. And then there is the locking R arbiter, which is transfer locking round robin arbiter. Basically, you can imagine that this arbiter by default might make this decision every cycle. So perhaps you get access to this resource for a cycle, and that's great. And that cycle tells you you've lost access. And some application that's maybe not a good idea. Maybe you want to get access to 2 or 4 cycles, whatever that number is. That's what you use the locking arbiter for. Um, okay, so like I said, the roadmap is we're going to demonstrate using the standard library arbiter first, and then we'll go ahead and write our own in a second. So uh, this module mostly exists to kind of wrap up the arbiter from Chisel, right? So right now it's the super spiffy locking round robin arbiter. We can try a few variants in a second. So what do we have? Okay, we have some number of inputs coming in, num ports. We have an output. We made all these decoupled, and the reason why, of course, is the arbiter itself has decoupled ports, so we're kind of trying to make it happen. Now, here's one thing we haven't seen yet in this course, but may become kind of common. So this arbiter has n input ports. This module has n input ports. So to connect all those up, we can use a for loop, right? So rather than having this, that's why it's parameterized, right? So I can have this n be anything, and they're going to do connections. Um, Now, these connections, we're using this bulk connection operator because it's going to connect all three sets of wires, right? It's going to connect the ready, the valid, and the bits, right? Because remember, the coupled isn't just one wire; it's those three things in that bundle. Um, and so that's kind of setting all that up. Um, then, of course, it's connecting up the output, and then for me to parse what's going on, I have some printfs here to kind of see what's happening. Okay, let's go ahead and fire this up. Um, and yes, go ahead. Yeah. So that's referred to as the bulk connect operator. If you have bundles on both sides, they'll connect all together the entire bundle. So the bundle, remember, can have lots of wires inside of it, and it'll try to put them together. It has some amount of smarts where even if the bundles aren't exactly the same, sometimes actually kind of can make it work. Um, there's a lot of additional bulk connect operators. There's some like, all sorts of weird symbols. This is the most basic one. This is the one we're using in this course. And yeah, if you have a bundle, in this case, the bundle is because it was a uint, but we made it decoupled. And so yeah, it's sticking all together. If we didn't have that, we would need to say, um, you know, otherwise we would need to have a much longer thing here. Say io.in, oops, uh, key dot, valid, and then it'd be a lot more work, right? Uh, they would need the valid, I would need the bits, um, and actually I got this backwards. I would need to be on this side. Um, Oops, I should save one of these for ready. So you can see like already that bulk connect operator is going to help us out some, right? Otherwise it would need to be ready, ready, and this one I need to flip around again. So um, oops, and I also forgot to put in, yeah, so you can see that single line kind of innocuously is replacing like 3 lines, right? In this case, it could be a lot more. So the bulk connect's super helpful. And that's kind of saving some space for us there. So I'll take it out for now, but we'll show in a second it's going to work. Cool. Other questions? Um, let's then run this test bench. So in this test bench, what are we doing? We are instantiating a module, sure. We're going to set the output to always ready, so that way to worry about is the output even ready at all. And then uh, for 5 cycles, this is me being a little clever to test bench because I'm just kind of being concise for a lecture slide. I need to set the ports, right? So for every port, I'm going to set the bits to be the port number, sure, whatever. But then for valid, as in is this port making a request? I do some math based on cycle. All that matters for now is basically you can see that some ports will initially not make a request, some ports eventually will make a request, right? Okay, let's kick this thing off. So we're kind of counting on our printf to see what happens. And so basically, you can see that originally, we have all 4 ports requesting, and then, port 1 wins. As time goes on, we have fewer ports requesting, and then port 2 eventually wins. Let's start tweaking this. So for example, instead of doing a locking round robin, what if we just did the OG, which doesn't even require that field? Great. All right, so the basic arbiter, remember, has fixed priorities. So you can see now that, since port 0 is making a request, port 0 is always going to win. Since port 0 is not making a request, port 1 is now the highest requester. Highest in the sense of priority, of course, it's numerically lower. Port 1 wins, right? Turn that one off. Then port 2 wins. That one wins. And you see, eventually, for example, at the end, when we have nobody making any requests, the valid bit on the thing is invalid because nobody's getting anything, right? So, yeah, that's an example of the original one. Let's kind of play around with it a little bit. Yes, go ahead. Yeah, I'll come back to locking in a second. Before we do locking, I'm actually gonna do round robin and work our way back to there. So I'm gonna, for now, uh, just turn them all on. You see, yeah, fixed priority, port 0 always wins. So now to your point, let's start modding this, right? So my memory is like a goldfish. So what is this? Round robin arbiter, RR arbiter. Okay, RR arbiter. So now we're turning on the round robin. So we had all zeros with priority based. With round robin, we see yes, it does change. But as you can see, it changes every cycle, right? So then the question you had was, okay, well, with that locking round robin arbiter, what about that? So let's go ahead and put that back in there. And if I put this to 1, that cycle grant, it should look the same as the round robin. I guess it maybe rotated it by 1. I'm not sure if my memory is that good, but still it's rotating, right? Meanwhile, if I was to make this longer, it's going to still do a round robin. It just should be holding it. Oh, I got to run this again too. It's just hanging on to it for the reservations are now longer, right? And so, yeah, that's that example. We can still kind of keep playing around with things a little bit. So, for example, you saw me have this for loop connecting things up, um, and that for loop was better than the alternative. The alternative should be functional, uh, or maybe I got a connection wrong. Oops. I got connection so wrong I crashed my Scala kernel. Let's spend a second looking at that and figure out what I got wrong. io.rec key.valid. Oops, I got these on the wrong side. So yeah, connecting things on the wrong side broke the Scala kernel. We're gonna relaunch that in a second. Don't worry. I'm gonna go ahead and fix this first. Um, yep, I got these 100% backwards, right? The input's on the left, right? And so then this one's also backwards. Okay, so we'll go ahead and get that there. And then now I need to go. Might be easier if I just like literally restart the whole Scala kernel. reload in the boilerplate, go back to this example. Okay, this time it did not break it, and this time it has the same apple we saw a second ago. So yeah, you can see that the bolt connect allows us to turn those three lines into one line, or I should say two lines, where we have the for loop as well. So the other question, of course, is, well, what's this other line I have commented out down here? Uh, that is me doing a super bolt connect. Let's see if that works. Uh, and the answer is yes. So that's connecting a zillion freaking wires, right? It's connecting two VEX, and each of those VEX, the elements themselves are bundles, right? There's a lot of stuff connected in just one line. Um, so yeah, the bulk connect operator is pretty freaking spiffy. Um, the reason why in the lecture slides I originally had this version up here was this pattern of using a for loop to kind of go through a VEC is very common. Sometimes the VEX line up perfectly, you can just do the bulk connect. Sometimes they don't quite line up perfectly, you got to do a for loop. But I just kind of wanted to show that example. Like I said, I have some magic with the printf to kind of show what's going on internally. But mostly we're just kind of showing these arbiters in practice. And we saw a second ago, they only really get interesting when everyone has simultaneous requests. So there's only some requesting, it's easier to kind of determine who wins. Cool. Other questions on the behavior so far? Yes. Where is io.in defined? Let's go back in the code and figure that out. Um, so yeah, so let's kind of go through it. So IO, it refers to the IO for the module. So that's, these io.rec, io.out, that's where they come from. Now, the arbiter itself is also a module. This bit of code here is some boilerplate you got to kind of use in order to like instantiate a module in Chisel. So arb uh, itself has its own IO. So arb's IO is .in. And this says one of the things where if you were unsure of that, yeah, we go ahead and oops, that's cool. I didn't mean to do that one. Let's just get it here. And yeah, it's going to have IO. And here's an example kind of showing you, yeah, it has IO connected up. Um, but if you weren't sure, you go ahead and even like, read the chisel docs for IO, and you can see it has it in and a chosen and this kind of stuff. No problem. Yeah, the questions are always appreciated. Thank you. Cool. Sure. Oh, yeah, good question. So what ID to recommend? I recommend IntelliJ. It's made by JetBrains. There's a community edition, which is free, and that's sufficient functionality for this course. Uh, yes, yeah. So IntelliJ has all those nice IDE features of, showing you the completions that make sense. It'll underline things that are syntactically wrong, so that way you need to wait till you compile. It's a pretty nice IDE, has a lot of smarts to it. It may seem very complicated, but it's one of these things where it's like those developers making that product are very keen to respond to community, so it's a very functional product. Um, that's the recommended thing. I know a lot of students love not IntelliJ, sorry, VS Code. And so for that scenario, there's a way to use something called Scala Metals to get some of that behavior into VS Code, right? So Scala Metals lets you run a process in conjunction with VS Code, lets you get to some of that same IDE kind of functionality. So you get the completions, you get the syntax warnings. There's a link to Scala Metals on the tools page for the course. Um, and that's not even counting like AI assistance or anything. Yeah, it's pretty cool. I recommend either using Scala Metals as the method of your choice or IntelliJ. Doing neither, I mean, it's just more work, right? And the spirit of this course is, make tools do the work. And unfortunately, Scala and Java are very verbose languages, but on the plus side, tools also very good at helping you autocomplete them. Um, cool. Yeah, that's a good conversation. Cool. So we demonstrated this arbiter. We've seen how it behaves. So maybe out of curiosity, actually, no, we'll come back to this in a second. What if we built our own? Right? And so this diagram's a little confusing, but let's kind of talk our way through it. So ultimately, what does this arbiter need to do? It has some number of ports. And for those ports, they all make requests. And so the kind of the key functionality is that somehow we take n requests and have one winner. How is that going to happen? Well, for the one we're building here, like the basic arbiter, we're going to use a priority encoder. So the center of that design is a priority encoder kind of taking all these requests. In this case, these requests are the valid signals of the port. So the way kind of like the Chisholm module structured it, you just have a port going to the arbiter. And so the arbiter is not just an arbiter, it's also an arbiter slash mux, right? We're kind of also, it's not just telling you if you got your request received, right? In this case, right, it's indicating a dot ready to you. It's also telling you, it's also going to actually do the muxing. So now, for example, now you can see how the things kind of fit together, where we have a priority encoder, so we're taking all these requests. Based on the priority encoder, of course, we can steer the right input in the mux, and we also can tell the right person that they actually won the grant. And I manually drew some logic gates in here to kind of try to show some scenarios, right? For example, um, if the output's not even ready, uh, nobody's going to get anything because they're not going to win, right? And so you kind of see how this comes together, where it's like, uh, it's a little bit unclear, but basically, this is a n-bit bus coming out of here, but it's one hot, and you can see with one hot, it's nice because you send just one wire at a time to these AND gates, and then we can make this kind of work. Or basically, if your thing has been requested and the output's ready, it comes together. This OR gate here is kind of seeing, are there any requests? If there's no requests, then nobody should be getting a ready signal or anything. So the thing I was talking about 5 minutes ago, where yes, there's a path now from valid through this logic gate, through that logic gate, back to ready. But it was kind of inevitable in this case. So let's code this up. And despite how scary that diagram is, this coding actually isn't the worst thing in the world, right? So starting off with the I/O, our vector of ports, yeah, we added decoupled for the ready valid signaling. Output, sure. To make some of the future stuff easier, I'm going to make these wires that are vex, right? So in other words, I'm going to go ahead and go through all the ports. I'm going to grab all the valids and attach them to this invalid thing. I'm going to go through all the bits and attach them to this bits thing. I'm also going to set all the input ports ready signals to false. Whoever wins is going to need to have theirs changed to true later on. That's that, last right wins thing we talked about earlier, last right semantics. Okay, so we kind of, at this point, just kind of grabbing wires. And then how are we actually making the choices? Well, we're actually just feeding in these wires directly into the priority encoder. And the priority encoder is making a choice. And I'm using this OH notation that indicates one hot. So that's both a convention used in the Chisel standard libraries, convention using in this design. So we have this one hot of who won. Um, and then what do we do with that? Well, we have the mux one hot we saw in the prior slide using the one hot chosen to actually route the data. Okay. And then remember in the prior slide we said, oh yeah, this out valid uh, is going to be the OR of all the input valids. So that's what this is. So this is one thing I haven't covered yet. It was on the Chisel cheat sheet if you were looking closely. Dot OR big R. So it's OR as in like a logical OR, and then the big R stands for reduction. So reduction is something that happens when you have, many things coming down. So given, in this case, n wires, it just ORs them all together. Unbeknownst to us, that could be one massive OR gate. It could be a bunch of pairs of OR gates in a tree. We're not specifying that. We're giving the tools a little freedom on that. Um, but yeah, it's doing an OR reduction for that. And then we are going to need a mark over one true. So one way it could be to kind of match like the prior slide with the AND gates. Alternatively, what I chose to do here is to acknowledge when a fire occurs. So io.fire means that both io.out ready and valid are both true. So ready comes from the actual output. We can't control that here. And the valid, of course, is set by this thing here. So in other words, if we have a valid request, anybody makes a request, there's at least one request, and the output's ready, this is going to fire. And then the question is, well, who's going to be told they won? The answer is whoever was chosen. So in this case, we chose to, unencode from one hot back to a uint, which is what this chisel standard library thing does. So we get this, log n bit signal telling us who won, and that's the one we go ahead and mark as ready. So this is one way of doing it. Um, it works. We'll come back to this design in future lectures and continue to find ways to write this code more concisely with more fancy operators. But functionally, it's all there. Um, and so we will tweak that in just a second on the next slide. But before we do that, any questions on this version of the implementation? Let's go ahead and tidy this up, right? So um, if you kind of saw what we're doing here, we spent all this time building up these wires and vex and pulling these things out and then attaching to the priority encoder and et cetera. What could be cleaner than that, right? Well, um, one thing we can do is uh, we can do like we showed in the actual diagram and set the ready bits to be based on the output of the priority encoder and the AND gate, right? So that's kind of going back to this. Like I said, actually having that AND row of AND gates here, that's what this is showing. So cool. That's there. So that removes the need to have that unencoding of the one hot encoder. Notice how because these are wires, we can kind of attach things in orders that make sense to us, right? So we actually declare all the input valids here. We attach them as inputs to the priority encoder, and then we actually set the inputs invalids over here, right? That's totally fine. Eventually, both sides of invalids are being used. And their stuff's kind of the same. This is a little bit more concise. Um, yeah, this also works. So here's another demo like we saw before. We can go ahead and fire this up and then actually, run this. And so, yeah, here's the same behavior we saw with the other original arbiter, which didn't have any persistence, right? Like before, if I was to have it be all things always requesting, we would see that, zero always wins. It's a fixed priority. But, we can turn this back on. Cool. Questions on that? Out of curiosity, what if we had the question, like we always do, of how in the heck did Chisel do this uh, with their version, right? So if we make this a regular arbiter, and then we print Verilog, let's see what we see. Obviously, a lot of stuff, but can I? There we go. Hit that button. Okay. Lot going on. There's an arbiter declared inside. Oops, let me turn off the printfs. Printfs always make a mess of this stuff. We do not need the printfs. Okay, printfs are turned off. Um, all of a sudden, it looks a lot simpler, right? Remember, first of all, it's only a you know two-port arbiter. But yeah, you can see the readies come in. Uh, some of the logic here is based on who gets the grant, but that's kind of really it. That's kind of the core of the arbiter right there, and then the rest of this is just kind of all wiring stuff up. If I was to make this maybe let's say a four-port, now I start seeing some of the priority encoder logic like we saw before in the prior lecture, how it's kind of implemented. Cool. But yeah, I mean, you're starting to see kind of, like you're saying, generators. This is what we're talking about, where we have, all this parameterization, changing the reports. It's not just changing ports, it's changing like the internal structure accordingly. And, you know, get it working however you can the first time, and then, look for opportunities to kind of simplify your code and make it more readable, etc. Cool. Let's, we already kind of printed it all out. Cool. Well, let's go ahead and move on to a crossbar. So now we have an arbiter. You see, you kind of building way up, right? We start off like a priority encoder, use a priority encoder to build an arbiter. Now we have an arbiter. We're going to build a crossbar. So a crossbar is a networking component in hardware, and you have some number of inputs, some number of outputs. And with a crossbar, any input can reach any output. Now there's something called a blocking crossbar, in which case maybe there's some limitations on that, but we're not doing that. This is full and non-blocking, right? Any input can reach any output, and so that should cause a little bit of head scratch for some people because wait a second, if I have any input port can reach any output port, that means multiple input ports can request the same output port, and then we have this need for arbitration, right? We have a situation where who gets actually sent to the output port. So guess what? What we're going to do in our design, you see in this drawing, we're going to put an arbiter on every output port, and then just send wires from every input port to every arbiter for every output port. So there's a lot of wires internally, but in terms of actual logic, the logic is kind of constrained to the arbiters for every output port. So they kind of convey, progress or no progress. We're using decoupled everywhere, right? They kind of ready valid and they kind of communicate, you know, yes, I have data to send, and the other end's going to respond. You know, are they actually receiving that data? Are they actually ready for it? And what are ready could be is the actual output itself ready, or it could be that the output is ready, but someone else is requesting this port, and they have a higher precedence according to the arbiter, and you haven't won the grant, right? Okay, so then uh, we're going to start building up a whole world here. So first, in our network, we need a message type, right? So our message is going to have an address of who we're trying to message. So given some number of outputs, I can identify them all with, log number, log base 2 of that number of outputs. So this is some, 2-bit field. If I have 4 outputs, which where I'm trying to go. Then there's the actual payload, the actual data. I'm going to define the IO here. You don't need to define it inside the module. You can define it outside the module for convenience. So it's a bundle. So yeah, we have a vec of inputs. And of course, they're of the type message, and they're decoupled. And because they're inputs, we're flipping it. Meanwhile, the output is also type message decoupled vec. Sure, cool. We got that. We're building stuff up. And here's the actual crossbar. So wait a second. So crossbar, okay, number of inputs, number of outputs, payload size. Here I am, instantiating that bundle we just made for the crossbar arrow with, those parameters we just talked about. What about the arbiters? Well, we need to declare n arbiters. For this version of the code today, I'm using seek.fill. It says, no reason I'm using seek, right? I want n things, but because this addressing is not happening in the hardware, we should use a Scala collection rather than a Chilla collection. Okay, so seek.fill, number of outputs. For each output, I'm declaring a module. In this case, we are deciding to do a round robin arbiter for fairness. Sure. Um, and cool. And notice how the round robin arbiter takes in the type for what type is going through the arbiter. In this case, we're saying it's going to be the message type, and each arbiter is deciding between a number of inputs, right? So go back to the diagram, right? So one arbiter per output, and it's choosing between however number of inputs we have. Okay, let's go keep looking at this code. Great. So you can see here I'm using these for loops to kind of iterate through all those zillion wires we got to wire up, right? So for example, for every input, I'm going to grab all the, I'm declaring a vec here, and I'm going to go ahead and grab all the readies um, from every arbiter. So remember, ready is going from the arbiter back out to the input, right? And so then we're grabbing all those and pulling them back out. Cool. And then for every output, I now need to connect every input to every output. So this is nested loop. There's a zillion wires in here. And thankfully, we have things like, bulk connects. We also have this interesting challenge, which wasn't shown on a diagram, but I'll go back to kind of talk about it anyways. So it's because this input is making a request. Remember, it's input from the point of view of the outside. It just sees a message going in. The message has an address field inside there, and it's ready valid signaling. The actual fact that that information is being, effectively broadcast to every arbiter is something inside to the crossbar. And so the reality is, as an input, you actually only want one arbiter to take your request seriously. So that's the one that's actually you're requesting. So, we're having that comparator basically saying, oh, in the message, what are you requesting, right? And so that's what that comparator was. We were just looking at. So yeah, you are requesting whatever port we're talking about actually matches the output port we're talking about. Cool. And oh yeah, is it actually valid, right? If it's not valid, we shouldn't even be bothering the poor arbiter. Um, that's all wired up, putting his AND gates in there. We wire up the outputs. And oh yeah, like before, I have some printfs. So um, here in 18 lines of chisel here and 6 lines of chisel there. We implemented the crossbar. It's parameterized by number of ports. input and output or independent number of ports, as well as the message payload size. Um, this is quite concise, right? This would be oodles of code in Verilog to just do one set of numbers, and here we're doing this for arbitrary, right? Um, and we'll see as future lectures, we actually can further simplify this code. So right now we have these kind of pairs of nested for loops. It works. We can talk our way through it. We'll see ways to make this even more concise and more elegant. But yeah, I'll admit this is complicated. So if you look at this the first time and kind of a little blown away, it's not just you. Um, if we go ahead and run this, here's kind of this notation of which port is receiving. So this is port 0, port 1. This is showing the valid bits, and you can see that, yeah, we make this test bench easy to read. The payload we're sending is what port is sending it. So we see, for example, the output port 0 is rotating between input ports 0 and 2. Output port 1 is rotating between input ports 1 and 3. Who wins? And you can see, well, who are we trying to message in the first place? Well, whatever the input port is, mod number of outs, right? And you see this behavior because I chose to use the round robin arbiter. Of course, if I didn't use the round robin arbiter, we would see a different behavior because static precedence. But yeah, so this is an example of this, and hopefully this is kind of showing how here we are designing an abstraction and using that as a building block to build an even bigger abstraction, right? We started off with things like, one-hot encoders and priority encoders, and worked our way up to arbiters. Now worked our way up to a crossbar. So this is kind of just building this library of generators, functionally kind of constructing more and more sophisticated hardware. Cool. Any more questions? Okay, let's stop.